again. So this is lecture 2 on series. We're going to talk about geometric series. For my students, we're still in section 11.2 of the textbook, which for those of you who are just turning in is Stewart's calculus. We just defined what it meant for a series to converge, and we actually used geometric series as an example. And I want to come up with a general formula for geometric series and how to work with them. But first, let me note something. When we define series, we start at the index with the lower limit I equal 1 to infinity. That lower limit can be any integer you want. It's just whatever integer you start with, you go through all of the integers from that point on. So if I start with I equals 0, my first term in the series is going to be r to the 0. The second term is going to be r to the 1. The third term is going to be r squared, and so on down the line, which of course in this case is 1 plus r squared plus r cubed, assuming, right, according to our definition. And here I'm just assuming r is just some fixed real number, r a fixed real. So this is your standard geometric series here. It's some fixed real numbers raised to higher and higher powers that we're adding up. And as we discussed before, that series is going to converge if this limit of partial sums here converges to something finite. Of course, the limit of partial sums is the limit of these things here. Those are the partial sums. Now, you may recall from the last video that we came up with a nice factoring of 1 minus r to the n. We noticed that 1 minus r to the n over 1 minus r is almost what we have here. Or in other words, 1 minus r to the n plus 1 over 1 minus r is equal to that sum. You should multiply it out. You should try multiplying 1 minus r times the sum here to make sure it does simplify to 1 minus r to the n. But with that in mind, this limit here is going to equal the limit as n goes to infinity of 1 minus r to the n plus 1 over 1 minus r. Oh, what's that limit equal? Well, it depends on what r is, right? Let's look at this. If r is equal to, say, 1/2, which is what we did before, 1/2 to the n plus 1 goes to what? It's going to go to 0, right? If r is equal to negative 1/2, as I take higher and higher powers, I'm bouncing back and forth between positive and negative, because negative 1/2 to a positive power, to a even power is going to be positive, to an odd power is going to be negative, but the absolute value of it's getting closer and closer to 0, so it's getting closer and closer to 0. What about 3/4? Same there. In fact, if r is less than 1, if the absolute value of r is less than 1, then r to the n plus 1 is going to what? Yeah, it's just going to 0. If absolute value of r, well, we can't have r equal to 1. Let's just put this little caveat, r not equal to 1 here. We'll look at 1 separately. If r is equal to negative 1, that's going to bounce back and forth, right? If r is equal to negative 1, that limit's not going to exist. We'll look at that separately too. But what's happening if the absolute value of r is bigger than 1? Well, then this does not converge, right? This either goes to infinity or bounces back and forth without converging between positive and negative. In other words, diverges. So this sequence here, this thing here, if absolute value of r is less than 1, that means r is between negative 1 and 1. This is going to go to 1 over 1 minus r. If the absolute value of r is less than 1. If the absolute value of r is bigger than 1, it diverges. So we've come up with our first formula. In fact, it's going to be bigger than or equal, and we'll point that out. So when we've come up with our first formula, let's write that separately because it's really quite an important formula. The sum I equals 0 to infinity of r to the I is going to equal 1 over 1 minus r if absolute value of r is less than 1. It diverges otherwise. This type of series is called a geometric series. Very important type of series, partly because we've got such a nice formula for it. We'll find out later that not all series have this nice little rule about whether it converges or not and what it converges to if it converges. So this is a particularly nice series. But let's just take a moment and point out that when r is equal to 1 or negative 1, it definitely diverges, just to make certain we understand this. So if r is equal to 1, we're looking at this series, which is 1 to the 0 is 1, 1 to the 1 is 1, 1 to the 2 is 1, so on down to 1. You just add 1 to itself over and over again. And as I keep adding more and more terms, this is just going off to infinity, so that diverges. So if r equals 1, it diverges. And let's just look and see what happens if r equals negative 1. We're going to get things that look like 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus dot, dot, dot. Now, you might want to say, well, it sure looks like that should zero out, but let's just look at the partial sums. The first partial sum, S1, is equal to 1, right? That's just 1. S2 is going to equal what? 1 minus 1, which is 0. S3 is going to equal what? 1 minus 1 plus 1, which is 1. S4, yeah, you guessed it, 0, so on down the line. So the sequence of partial sums is a sequence of 1, 0, 1, 0, 1, 0. That diverges. That doesn't even go off to infinity. That just diverges. It doesn't zero in on anything, so this diverges as well. Okay, and in the next lecture, we're going to look at examples of how to use the geometric series to find sums of series that are similar to geometric series, related to them in some way or another. And okay, good place to stop. Bye.